Joining us for this second video in the alkane reaction series, where today we're going to be discussing the radical halogenation reaction mechanism. Okay, and as we go through it, I hope this meme here will actually make sense to you. This is depicting how propagation works. It's kind of like a propagation of violence, but in the chemical sense. Okay, so here's maybe perhaps the easiest, simplest radical halogenation reaction example, and I just want you to know this is always going to need some sort of light source. Okay, and then you notice this simplest alkane methane is halogenated, monohalogenated by chlorine atom molecule, excuse me. And then here we're gonna be thinking about some thermodynamic implications of this reaction. Okay, and I think if you go look at the thermodynamic data table in your textbook, you should be able to look all these up. In the methane, the CH bond is has about 105 kilocal per mole of bond dissociation energy. That just means, like, if you want to break that bond by some sheer energy, it takes about that much energy, 105 kilocal per mole. It's really like a way of describing how strong of a bond is. So you could see that CH bond is much stronger than the Cl-Cl single bond, which is only worth 58 kilocal per mole. Now C carbon chlorine bond is worth 85 kilocal, while HCl is worth 103 kilocal per mole. Okay, so if you ask how do you know those numbers, that would have to be obtained experimentally or given to you in a table or something. And then to calculate the delta H of this, what you would do is, right, like you could just sum up all the dissociated bonds, or BDEs, BDE energies of the bonds that are broken in the reaction. Namely, this bond is broken, right, and then this bond is broken, this bond is formed, this bond is formed, and then you subtract the sum of all the BDE energies of the formed bonds. Then what do you get? That would be the delta H, right? Like, if the thought process is this, because if you are forming much more stable bonds than the bonds you broke, then that it's gonna be a good thing for delta H, right? So that's the idea. So let's calculate that real quick. So the bond being broken, of course, I'm gonna skip writing the units here, even though that's kind of wrong. And I'm gonna add up the energies of the bonds that are formed in the reaction, subtract one from the other. This comes out to be negative 25 kilocal per mole. What does that mean? That means this is going to be enthalpy driven reaction. Because the enthalpy is negative, that means it's a good thing, right? That's favorable reaction, enthalpically speaking, energy wise. And you could see this is not entropy driven, even from the reaction equation, because you start with two particles, you end up with two particles, so there's no favorability in terms of entropy factors. Now, how do we know the reaction mechanism for free radical chain reaction? And it is a chain reaction because one free radical is generated, and that's going to propagate and starts this chain reaction that will not end until some sort of termination event happens. And this is something it's good to sort of apply to any reaction mechanism. This thought process of how do we know what the reaction mechanism is? It needs to be at the end of the day based on some sort of experimentally verifiable observations. Otherwise, it's not science, right? And in this case, these are the three observations we could make. It needs heat or light to initiate that halogenation. In this specific case, we're thinking about chlorination, but this is going to be true for bromination as well and other types of radical halogenation. At least for chlorination reaction, we notice that that light that's needed is in the 400 to 500 blue nanometers. The blue wavelength range is most effective. And why is that? Why does that matter? Well, this happens to be the same wavelength, which is lambda, readily absorbed by the Cl-Cl bond. Okay, so that's what's significant about that particular observation. And then another observation is one photon produces many molecules of the product. That third observation suggests it's a chain reaction that just propagates itself. Okay, so to be able to explain all of these observations, what would have to be the mechanism? Okay, well, let's think about that. The first step must be some sort of include some sort of initiation mechanism. This explains the observations A and B. Okay. Well, as well as kind of C, but won't get ahead of ourselves. Now, oftentimes when a chemist writes about how light is needed, the light energy can be mathematically described as h nu. If you recall from Gen Chem, E, or energy of light radiation, is h nu, Planck's constant multiplied by the frequency of the light, right? So that seems to initiate radical formation, which is also called homolytic cleavage. We talked about homolysis last time, but the homolytic just means two atoms get the same amount of electrons, one each, as opposed to heterolytic cleavage, where one atom gets 2 electrons, the other gets none, and gets a positive charge and whatnot. Okay. And then as a result, you get chlorine, 2 chlorine radicals, which, right, is the same as drawing that, but just to save time, I'm just writing that one dot or electron. I want you to assume that the 6 electrons are there as well, and this is a free radical. Okay, that's not trapped in anything. This is a very rare event, even with sufficient light energy, because these things are very reactive. It's a endothermic event. You have to pump in energy for this to happen, right? It's an uphill reaction here. And then to explain C, there has to be some sort of the observation C, that is, there must be some sort of propagation step. That means when you go through this reaction mechanism, in the end, we need to be left with yet another new radical species so that the reaction just cannot end. It just has to keep going with just the presence of one photon splitting one molecule of chlorine should be enough to convert a bunch of molecules. That's what this mechanism has to explain. So far what we have in the mixture is this one chlorine radical and a bunch of methane molecule in the reaction vessel, if that makes sense, right? So this chlorine radical, how would it react? It could react as a radical to extract hydrogen radical or hydrogen atom from methane. And then if it does, right? Hope it makes sense that these arrows are showing two electrons are involved to make HCl bond, while this is a homolysis, so one electron goes to the carbon. So you end up with this methyl radical. We could say that this is the propagated radical, because chlorine ceased to be a radical through this mechanism, and that's the driving force for that step, and yet you created a new radical here, right? So remember, this is a rare event, so there's only like one chlorine radical atom in the whole reaction mixture, a bunch of methane. What else is there that's abundant in this reaction mixture? Well, that would be the chlorine molecule that's not radicalized. There's a bunch of those. So this could react with that radical. And that would leave behind a chlorine radical, right? Remember that there's very few radicals. So they won't run into each other at the beginning. Most of the molecules in this mixture are intact molecules like chlorine or methane molecule. Okay, so this is now, of course, the product. And then you have the further propagated chlorine radical. Right, and then this is gonna react just like earlier over here with another methane molecule and whatnot. So this is what we mean by chain reaction. Continues until you run out of methanes and chlorine molecules. Okay. Now in reality, right, this chloromethane can further react to form things like dichloromethane or chloroform or even tetrachloromethane, etc. Until basically you run out of methane and chlorine molecules. Now, in the end, all good reactions have to end. So how does it end? When the reactant concentration, that's what the bracket means, remember, gets low, right? Then it's possible that some radicals can run into each other, like maybe the two chlorine radicals will run into each other. And then there's no more radical, so the reaction ends, or it's possible one of the methyl radical that's propagated could run into chlorine radical. Then again, the radical is not propagated, so the reaction ends. Or often the case, it is that the radical just reacts with eventually. Well, maybe that's not good. The wall of the reaction vessel, like a glass, okay, because it's so reactive. Once there's not much methane for it to react with anymore, what could happen is this could just react with glass or glass molecule, which is silicon dioxide, and chlorinate that. And either way, what this does is these types of termination steps end up with no more radical, and that's when the reaction terminates. Now, what I've seen that's a common mistake with students is that they show the termination reaction as the second step, or a propagation step. In the majority of the reaction must be happening through this propagation step, where a radical is reacting with non-radical, radical is reacting with non-radical. That needs to keep going. Otherwise, there's no way that the whole reaction finishes to convert most of the study material to this halogenated product. Propagation has to be the mechanism, right, to explain that. So don't show the termination steps when you should be showing propagation step. Hope that makes sense. And in the next video, we're going to be talking about the regioselectivity of these reactions.